Hello, and welcome to Astronomy for Sleep, a quiet place to drift through the universe at a gentle pace where the night feels wide, the language stays simple, and the questions can soften into calm. Tonight, we are going to follow a problem in modern cosmology that is famous not because it is loud or dramatic, but because it is persistent. It is the kind of problem that does not disappear when people stare at it harder. It does not vanish when new telescopes arrive. It does not resolve itself after one clever paper. It simply remains a small mismatch between two ways of measuring the same thing, a mismatch that has held steady long enough to become a real mystery. This is the Hubble tension, the problem that will not go away, and it is a perfect subject for a slow, sleep-friendly journey, because it asks us to think about distance, time, light, and the deep shape of the universe not with urgency but with patience. The Hubble tension is not a threat. It is not a countdown. It is a signal that our measurements are now so good that the universe has started to show us where our simplest story might be missing a detail. To begin, we need one calm, solid idea, the idea the tension is built around. The universe is expanding. On the largest scales, galaxies are moving away from each other, not because they are flying through space like shrapnel, but because space itself is stretching. When astronomers measure light from distant galaxies, they find that the light is redshifted. The farther away a galaxy is, the more its light is shifted toward redder wavelengths on average. This is one of the great discoveries of modern astronomy. It tells us the universe is not static, it is evolving. And once you accept expansion, you can ask a natural question: how fast is it expanding right now? The number that answers this is called the Hubble constant, usually written as h0, and it expresses the expansion rate today. In simple terms, it tells you how quickly distance is being added between us and a galaxy per unit of distance. The bigger the Hubble constant, the faster the expansion today. If there were only one way to measure the Hubble constant, there would be no tension. But there are multiple ways, and the two most important categories are conceptually very different. One way is local meaning. It tries to measure the expansion rate directly in the nearby universe, using distances to galaxies that are close enough to be measured with relatively direct methods. Another way is early universe, meaning it uses the cosmic microwave background, a relic of the early universe, and infers what the expansion rate today should be by fitting a cosmological model to that early snapshot. In a perfect world, these two approaches would agree. They are measuring the same universe after all, but they do not. The local measurements tend to give a higher value. The early universe inference tends to give a lower value. That difference is the Hubble tension. Before we go deeper, it helps to pause with a gentle truth about cosmology. Measuring cosmic distances is hard. We cannot stretch a tape measure across the universe. We read distance from light, and light is complicated. It is altered by dust. It is affected by the physics of stars. It is filtered through instruments. It is shaped by the expansion of space itself. Every distance method involves assumptions and calibration. So whenever two methods disagree, there are two broad possibilities. Either the underlying cosmological model connecting early and late times is missing something, or one or both measurement methods contain subtle biases that have not been fully accounted for. The tension does not tell us which possibility is true. It tells us that one of them might be, and that is why the tension is so interesting. It is not a problem that says everything is wrong. It is a problem that says something is slightly off, and the universe is daring us to find out what. Now let us take the local approach first, because it feels more intuitive. If you want to know how fast the universe is expanding today, you might try to measure distances to nearby galaxies and compare those distances to their redshifts. If you plot recession speed versus distance, the slope of that relationship gives you the expansion rate. But distance is the hard part. How do you measure the distance to another galaxy? The most famous approach uses what is sometimes called the cosmic distance ladder. It is called a ladder because it is built in steps. You start with the nearest objects where you can measure distance using geometry, then you use those objects to calibrate a class of standard candles objects of known intrinsic brightness. Once you know how bright something truly is, you can measure how bright it appears and from that infer distance, because brightness falls off with distance. In practice, the ladder often uses stars called Cepheid variables as a key rung. Cepheids are stars that pulsate with a regular period, and there is a well-known relationship between a Cepheid's pulsation period and its intrinsic brightness. If you calibrate that relationship using Cepheids close enough to measure geometrically, then you can use Cepheids in other galaxies to measure distances to those galaxies. Then you can use those galaxies to calibrate an even brighter class of standard candles, Type 1a supernovae. Type 1a supernovae are explosions with fairly consistent peak brightness after certain corrections, making them visible across much larger distances than Cepheids. So the ladder goes from geometric distances to Cepheids to supernovae to distant galaxies, and with that you can measure the expansion rate in the relatively nearby universe. This method has been refined dramatically. It uses exquisite measurements from space telescopes. It uses careful statistical techniques. It tries to account for dust and for differences between supernovae. And in many studies it produces a Hubble constant around the low to mid-70s in units of kilometers per second per megaparsec, meaning per large cosmic distance unit. The exact number is not as important tonight as the fact that it is consistently higher than the early universe inference. Now let us turn to the early universe method. This one begins not with nearby galaxies, but with the cosmic microwave background, the CMB, the faint radiation that fills the sky in every direction. This radiation is a snapshot of the universe when it was about 380,000 years old, when it cooled enough for atoms to form and light to travel freely. The CMB is remarkably uniform, but it contains tiny variations in temperature that reflect small differences in density in the early universe. Those tiny variations are not random noise. They have a pattern. They include a series of peaks in the angular power spectrum features that reflect sound waves in the early universe's plasma. By measuring these patterns with high-precision, cosmologists can infer several parameters: the density of ordinary matter, the density of dark matter, the geometry of space, and the overall scale of fluctuations. When these parameters are interpreted within the standard cosmological model, the model also predicts what the expansion rate should be today. This predicted value tends to be lower than the local distance ladder value, often in the high 60s. So here is the tension in a calm sentence. The nearby universe seems to say expansion today is faster. The early universe seems to say expansion today should be slower. Both claims are supported by careful measurements. Both have been examined repeatedly, and the difference remains. Now, why does it not go away? If the difference were due to a simple mistake, the field might have resolved it quickly. But the Hubble tension persists because both measurement programs are deep, careful, and independent in many ways. Each has its own potential weaknesses, and each has been tested. When one check is done, the tension often survives. That survival makes it intriguing. It suggests either a subtle systematic that is hard to see, or new physics that changes the connection between early and late times. Let us explore the systematic side first, because it is the most conservative explanation. In the distance ladder method, there are many places where small biases could enter. Cepheids are not identical objects in all environments. Their brightness can be affected by metallicity, the abundance of heavier elements, which can differ from galaxy to galaxy. Cepheids in crowded fields can blend with other stars, making them appear brighter than they truly are. Dust can dim and redden light. Calibration of geometric distances can have subtle issues. Supernovae can have small population differences depending on the type of host galaxy. Selection effects can bias, which supernovae are included. Photometric calibration. The translation between instrument counts and true brightness must be extremely accurate. Even tiny shifts in these steps can alter the inferred Hubble constant. Researchers know this and they build careful corrections, but the corrections themselves depend on models and assumptions. A systematic effect can survive for a long time if it's embedded in method. On the early universe side, there are also potential systematics. Measuring the microwave background requires separating it from foreground radiation emitted by our own galaxy, such as dust and synchrotron emission. Instruments have noise and beam shapes that must be characterized. Data analysis choices can influence parameter inference. There is also the fact that the CMB does not measure the Hubble constant directly. It measures patterns that are interpreted through the standard model. If the standard model is slightly wrong, the inferred Hubble constant could shift. That is not a systematic in the simple sense, it is a model dependence. But it means the early universe value is not purely observed, it is observed plus models. This leads naturally to the new physics possibility. Suppose both sets of measurements are correct. Then the mismatch suggests that the standard model connecting early and late times is missing an ingredient. The standard model, often called lambda CDM, includes ordinary matter, dark matter and dark energy in the form of a cosmological constant. It assumes certain properties for neutrinos and other particles. It assumes general relativity describes gravity on large scales. It assumes the physics of recombination when the CMB was released is well understood. If the real universe differs in one of these areas, then the inferred Hubble constant from the CMB could shift, perhaps reconciling with the local value. Many ideas have been proposed. Some involve changing dark energy. Perhaps dark energy is not constant but evolves with time. If dark energy behaved differently in the past, it could change the expansion history and the inferred Hubble constant. Another idea is early dark energy, a brief period in the early universe when an extra energy component contributed non-negligibly, altering the sound horizon scale that sets the CMB's acoustic peaks. If the sound horizon was smaller than in the standard model, then the inferred Hubble constant could be higher while still fitting the CMB. Early dark energy is attractive because it targets the era the CMB is sensitive to, but it must fit many other data constraints, including galaxy clustering and other cosmological probes. Many early dark energy models have been tested and constrained. Some are still under discussion. Another class of ideas involves additional relativistic particles in the early universe, sometimes called dark radiation, which would change the expansion rate then, and the sound horizon. Another class involves interactions in the dark sector, perhaps dark matter interacting with dark energy or with other fields. Another involves modifications to gravity. Each idea tries to solve the tension while preserving the many successes of the standard model. And that is the challenge. The standard model fits a lot. It is not easy to change one part without breaking others. This is part of why the tension will not go away. It sits at a crossroads. If it is due to systematics, they are subtle. If it is due to new physics, the new physics must be subtle too, because the standard model works well. So the tension is like a quiet riddle that refuses to accept a loud answer. Now, one of the most calming things we can do is slow down and see how scientists are approaching this, because the approach itself is patient and methodical. In the local universe, researchers are developing alternative distance ladders and independent distance methods. One important alternative uses the tip of the red giant branch, sometimes abbreviated TRGB. Red giant stars reach a predictable brightness at a certain stage of their evolution, providing another kind of standard candle that can be used to measure distances. TRGB methods have different systematics than Cepheids, so they serve as a check. Another approach uses mesogalaxies where water masers orbiting supermassive black holes can provide geometric distance measurements through precise mapping of their motions. These distances are less dependent on some of the astrophysical assumptions of the Cepheid ladder. Another approach uses surface brightness fluctuations in galaxies. Another uses gravitational lensing time delays, where the time differences between multiple images of a lensed variable source can be used to infer distances and the expansion rate. These lensing methods have their own modelling challenges, because they depend on the mass distribution in the lensing galaxy and along the line of sight. But they are independent enough to be valuable. Another emerging approach uses gravitational waves as standard sirens. When two neutron stars merge, the gravitational wave signal encodes a distance. If an electromagnetic counterpart identifies the host galaxy, redshift can be measured and the expansion rate inferred. This method is still developing, but it is conceptually powerful because it relies on different physics. Meanwhile, in the early universe arena, researchers are also refining measurements. New CMB experiments aim to improve polarization measurements and reduce uncertainties. Large-scale structure surveys improve measurements of baryon acoustic oscillations (BAO), which provide a standard ruler linked to the sound horizon. BAO measurements combined with other data help constrain the expansion history. If the Hubble tension is due to new physics altering the sound horizon BAO, and related probes are crucial checks. Researchers also study the physics of recombination and potential subtle effects that could shift CMB inference. They look for consistency across different datasets and instruments. In other words, the field is not stuck. It is widening its measurement base. When a number is disputed, the way out is not to argue louder. It is to measure in new ways. That is what cosmology is doing. Now let us take a gentle detour into why the Hubble constant matters beyond being a number. It is not just a measure of speed. It is part of the universe's timekeeping. The expansion history relates to the age of the universe. It affects how long structures had to form. It influences the interpretation of distances across cosmic time. It ties into the densities of matter and energy. If the Hubble constant today is higher, it can imply certain differences in the expansion history that might ripple through other cosmological parameters. The tension is therefore not a small bookkeeping issue. It touches the core of the standard model. But the tension is also not a sign that the universe is unstable or that our understanding is useless. It is the opposite. It is a sign that our understanding is sharp enough to notice small mismatches. A century ago, we could barely measure cosmic distances beyond our galaxy. Today, we debate a few kilometers per second per megaparsec. That is a remarkable achievement. The tension is a frontier problem, not a foundational collapse. Another calming thought is that cosmology has seen tensions before. Many have been resolved by improved data or by refined understanding of systematics. Some have led to deeper insights. The discovery of accelerated expansion itself, which implied dark energy, was once surprising and controversial. Over time, it became a pillar of modern cosmology supported by multiple independent probes. If the Hubble tension is resolved by new physics, it might become a similar story, a new ingredient added to the model not to replace it entirely but to extend it. If it is resolved by systematics, it will strengthen the model and the measurement tools. Either outcome is progress. Now, to keep the restful, let us imagine the Hubble tension as a quiet disagreement between two clocks. One clock is in the present-day universe, ticking in nearby galaxies measured through distances and supernova light. The other clock is in the early universe, embedded in the microwave background's pattern of ancient sound waves. Both clocks are trying to tell us the same thing, how fast the universe is expanding today. But they disagree slightly. The question is not which clock is lying. The question is what hidden factor is making one clock run a little faster or slower, or whether there is a third influence neither clock has accounted for. It might be dust blending calibration or selection effects in the local clock. It might be an early universe ingredient affecting the sound horizon in the ancient clock. It might be something else. The universe is asking us to be more careful, and there is something soothing in that. The universe is not a puzzle that demands immediate resolution. It has been expanding for billions of years. It will continue expanding. Whether the Hubble constant is 67 or 73 does not change the fact that the night sky remains. But for scientists, the number matters because it is a doorway to deeper understanding. And for us tonight, the story matters because it shows how science handles uncertainty not by declaring victory, but by expanding the set of measurements, refining methods, and being willing to adjust the model if reality demands it. Let's also gently address a common misinterpretation that the Hubble tension means the Big Bang is wrong. It does not. The Big Bang framework, the idea of an expanding universe with a hot early phase, is supported by multiple lines of evidence. The tension is about the details within the standard cosmological model, not about the existence of expansion or the reality of the microwave background. If the tension leads to new physics, it will likely be a modification to the model's ingredients, not a rejection of the entire framework. If it leads to systematics, it will be a refinement of measurement. The broad cosmic story remains. Now imagine the near future of this puzzle, because it helps explain why it feels so persistent. New data will arrive from new surveys and experiments. Some methods may converge, some may diverge. The tension may sharpen or soften. If multiple independent methods begin to support the higher local value confidence grows, that the early universe inference must shift, perhaps implying new physics. If independent methods support the lower value confidence grows, that local ladder systematics are at play. If methods cluster into the groups with different values, the puzzle becomes more nuanced. This is how scientific mysteries evolve. They rarely end with a single dramatic announcement. They end with a gradual convergence of evidence. The Hubble tension will likely resolve in that way too, through accumulation rather than revelation. And while that accumulation continues, the night sky remains a quiet reminder that the universe is vast and patient. The same expansion that is being debated is what carries galaxies away from each other. The same early sound waves that imprinted the microwave background are what seeded the structures that later became galaxies and stars. The tension exists because we can measure these things so well. That in itself is a kind of calm triumph. We are small beings on one planet, yet we can read the expansion of the cosmos from tiny shifts in light and subtle patterns in an ancient background glow. So as we come toward the gentle close, let the phrase "the problem that won't go away" soften into something less restless. The Hubble tension remains not because science is stuck, but because the question is delicate. It sits at the edge of precision. It might be telling us about hidden biases in distance measurement. It might be telling us about new physics in the early universe. It might be telling us about the true nature of dark energy or other components. And even if the answer is mundane, the process of finding it will make cosmology stronger. The universe is not threatened by the tension. We are simply learning to describe it more accurately. Now, with the night settling in, imagine the two cosmic clocks again. One is here among nearby galaxies, measured by the brightness of stars and the flare of distant supernovae. The other is far back in time, measured by the faint microwave glow that has travelled since the universe became transparent. They disagree by a small amount, like two quiet ticking sounds that are slightly out of sync. And the scientific world is listening carefully, trying to understand why. That listening is slow, it is careful, it is patient, it is the opposite of panic. And in that patient listening there is something restful, the sense that the universe is not a chaotic surprise, but a system with deep order, deep history, and a steady rhythm that we can learn to hear more clearly over time. Thank you for spending this calm journey with Astronomy for Sleep. If you want to drift further, let the idea of expanding space become a slow breath, galaxies gently receding as the night deepens the cosmic microwave background surrounding you, like a soft hush, and the unanswered question of the Hubble tension resting lightly in the mind. Not as a worry, but as a reminder that even our best maps can become more accurate, and that the universe is always a little deeper than the simplest story we tell about it.